class. Welcome to Fundamentals of Chemistry. I'm Dr. Sujata Krishnaswamy. Today we will look at Rutherford's nuclear model. Before we venture into the model, we're going to look at the different types of radiations. Radiations are energy waves, and there are three major types of radiations. They're called the alpha, beta, and gamma radiations. The alpha radiations can be easily stopped by a sheet of paper. The beta radiation can go through our clothing. Gamma radiation can go through concrete and can simply go through the entire organic tissue. So between the three radiations, the gamma radiation is the more powerful radiation in terms of energy. Alpha particles or alpha radiations are nothing but helium nuclei without the electrons. A quick look at the periodic table will tell us that helium has 2 protons and 2 electrons. If you remove the 2 electrons, you're left with just the 2 protons, and this is nothing but the helium that is positively charged. So alpha rays are positively charged helium atoms with just the protons. Beta rays, on the other hand, are composed of only electrons, whereas gamma rays are just made up of radiation. So let's now move into Rutherford's nuclear model. We're going to start first with this experiment known as the gold foil experiment. In this experiment, a source of alpha particles is placed inside a lead block, and these alpha particles that come out of the lead block hit a very thin gold foil. Around the gold foil is a fluorescent screen that captures the radiation, and when reading the fluorescent screen you can get some data about what type of radiation, something about the nature of the atom, and so on. Rutherford and his students made 2 key observations. The first observation is that most of the particles went straight through the gold foil as though there was no obstruction. The second observation is some of the particles were deflected at small angles. So Rutherford asked his graduate students to repeat the experiment. As you know, the best scientific method is to repeat the experiment 2 or 3 times so you get consistent results. The second time the students repeated the experiment, they found that there was a third observation that they made. A very small portion of the alpha particles were deflected at very large angles. In fact, they made their way back to the source. That puzzled Rutherford, and they started to think about what the gold foil is made up of. So let's go back to look at what the alpha particles are comprised of. As I mentioned earlier, they're made up of positively charged helium nuclei, which means something that obstructs the alpha particles, stops the alpha particles in their path, must also be positively charged. Keep in mind that positive and positive charges will repel each other. The opposite charges will attract each other. So based on the 3 observations, Rutherford said that the plum pudding atom, the model, is no longer valid. So if you take a look at the plum pudding model, according to Thomson, the sphere is a positive charge. So if the alpha rays are positively charged, they cannot move past the sphere of positive charge. The positively charged sphere will obstruct the pathway of the alpha rays. So based on the first observation, where most of the rays went straight through the gold foil with no obstruction, Rutherford concluded that most of the atom is empty space. The second observation is that alpha particles were deflected at small angles, which means the positively charged alpha particles probably came very close to another positively charged species within the atom, which must be the proton. The third observation was the most important observation. A very small portion of the rays went straight back to the viewer, which means the positively charged alpha rays were on head-on collision with the positive charge in the atom. So based on this, came up with a model which is called the nuclear model. According to Rutherford, most of the atom is empty space. That's why most of the alpha particles went straight through the atom. All the positive charge is concentrated in a small sphere, which he termed as a nucleus. So when the positively charged alpha rays came very close to the nucleus, they were deflected at an angle. A very small portion of the alpha rays hit that nucleus straight on, and they were reflected at really large angles. The nucleus contains the positively charged particles called the protons. It also contains a neutral particle called neutrons. An important thing to note in the Rutherford's model is most of the atom is empty space. The nucleus is a very small portion of the atom. The protons and the neutrons are inside the nucleus. The electrons are outside the nucleus. So the nucleus is very dense compared to the rest of the atom. There's a lot of packing of subatomic particles in a small region called the nucleus. That's why when the rays hit the nucleus directly, it's a head-on collision, and because of the momentum, they just go straight back at the viewer. So here are the dimensions for the atom. It's 1 times 10 power minus 8, and you can see the dimensions for the nucleus is 10 power minus 13, so it's several orders smaller than that of the entire atom. So now we can summarize what an atom is made up of. It's made up of electrons. They're outside the nucleus with a relative charge of -1. Protons are inside the nucleus with a relative charge of +1. Neutrons are neutral. They're also inside the nucleus and they have no charge. When you look at the relative masses, the proton and the neutron are equal in mass, whereas the electron is a very light particle. Thank you for joining us today. I hope to see you again in the next episode where we will talk about Moore's model of the atom.